Jai Hind everyone, my name is Mukulit Goel and I am assistant professor in Department of MCA. Today I am giving a lecture on non-restoring division algorithm, which is a part of the subject for computer organization and architecture. Subject code is BMC 105 and this lecture is for MCA first year students. First of all, I want to discuss about what are the contents of my lecture. That is, what is arithmetic division, definition of non-restoring division algorithm, flowchart of non-restoring algorithm, example of non-restoring division algorithm, advantages and disadvantages of non-restoring algorithm, and how it is different and what is the difference between restoring and non-restoring division algorithm. So first of all, I will start with the arithmetic division. So normally what we do in arithmetic division, there are four main things, which is divisor, dividend, quotient and remainder. So when we do a binary division, we follow this rule, but when we do it in terms of binary, there is a division technique for unsigned binary values that simplifies the procedure by eliminating the restoring phase. In one of my previous lectures, I have discussed the restoring division algorithm, how it works and how we reach up to the final quotient and remainder, not using a division basically, but using a addition and subtraction of binary numbers. Basically, the division of unsigned numbers is done through a binary division, but through this algorithm we will not use the binary division. We do a binary division by using the addition and subtraction between the divisor and dividend. So the non-restoring division is a division technique for unsigned binary values, and it is a iterative approach that approximates the quotient and updates the remainder in each iteration. It has some steps, it has some 9 steps, and in 9 steps we come to know about how will we get our quotient and how will we get our remainder. So in step 1, the corresponding value will be initialized into the register, and the register A will contain 0 on initialization. Register M will contain the divisor, the register Q will contain the dividend, and N is used to specify the number of bits in the dividend. So these representation can be different in different algorithms, but for myself I use register A, Q, N and M. So in this bit, now first we initialize all these values, we initiate all these values, and then in step 2 we check the sign bit of A. What is the sign bit of A? Of register A is 1, then shift the value of AQ through left. So what we use left shift for performing the first iteration if the bit of A is 1, if the sign bit of A is 1, and perform A is equal to A plus M. And if this bit is 0, then we shift the value of AQ into left and perform A minus M. So in binaries there can be only two possibilities, either the sign bit value of A is 1 or either the sign bit value of A is 0. So when the sign bit value of A is 1, we update the value of A by using A plus M, and when the sign bit value of A is 0, we update the value of A using A minus M. So in the case of 0, what we do is the 2's complement of A, and then we added it into the register A. So the A is equal to A minus M can also be written as A is equal to A plus minus M. So it holds the same value and the result is stored into A. After this iteration, step 3, we again check the sign bit of A, and if we check the sign bit of A is 1, then Q0 will become 0, and if this bit is 0, then Q0 will become 1. So what Q0 indicates? The Q0 indicates the least significant bit of Q. So this is step 5. In step 6, after that the value of N will be decremented. Here N is used as a counter, and our calculation or algorithm will be stopped or finished when the value of N become 0. Okay. So after that we check the value of n, and we will decrement it by the 1, and we do these iteration till step 6 until we reach the value of n is equal to 0. When we reach the value of n is equal to 0, then we will go to the next step 8. Otherwise we will go to the step 2. Means till the value of n is equal to 0, we iterate till we get the value of n is equal to 0. So in step A, we perform a is equal to a plus n if the sign bit of of register A is 1. So after doing this last iteration, so we check that the value of register A contains the remainder and the value of register Q contains the quotient. So in this way, through non-restoring division, we find the division value of any number by not using the following the rules of division, binary division, but by doing the simple addition and subtraction in the value of the registers. So it will become more clear through its flowchart. So as per the steps, this is the flowchart. What we define the number of bits. A is initially 0 and A represents the accumulator. M is the divisor, Q is the dividend. We check the sign bit of A. If it is 0, we left shift AQ and we do A minus, A is equal to A minus M. If the sign bit of A is 1, we shift left AQ and do A is equal to A plus M. Again we check whether the sign bit of A is 0 or 1. If it is 0, we do Q0 is equal to 1, and if it is 1, when we do Q0 is equal to 0. So Q0 is the least significant bit. We decrement the counter by 1, and if decrement counter n is equal to 0, then we check the sign bit of A and do the last iteration, A is equal to A plus M. And after that we get the quotient, and if it is not n is equal to 0, then we do all these steps regularly till the value of n is equal to 0. So it will become more clear by using an example. So first I have to take the example of division restoring algorithm where dividend is 11 and divisor is 3. So the binary value of dividend 11 is 1011 and the divisor 3 is 00011. So we use 5 bits calculation division. So if we normally do 11 divided by 3, then what we get? We get 392. So the remainder represents 2 and the quotient represents 3. Okay. So what we have started, first we check the sign bit of A, which is 0. So what we do when the sign bit of A is 0, here A is this, A is equal to, which is initially 0. Okay, and divisor and M and Q is 11 and 3. So here it is representing 11 and here we are representing 3. So we begin with 1011, check the value of 0, and if the check the value of 0, what we have done? We have left shift A and Q, and what we have done? We have done calculation of A is equal to A minus M or A is equal to A plus minus M. So after this calculation, what we get? We get, first we do left shift. So after doing the left shift, what we have achieved, that our least significant of 0 has gone and we have shifted the each bit by 1. So here this one is this, 0 is this one is this, and it one is there, and we left the one space empty. So after this we do A is equal to A minus N. After doing A is equal to A minus M, we get the value and check what is the value of A. If it is 0, what we have do? If Q0 is equal to 0, so we have put a, if q0 is equal to 1, so we have put a 0. So we put a 0, and then again we do a left shift because the least significant bit is 0. So after doing the left shift, here it comes 1, and what for, if we get the 1, then what we'll do, we do a is equal to a plus m. So in next iteration, what we have done, instead of doing a is equal to a minus m, we have done a is equal to a plus m, and after getting this, what we get 1 1 1, and as we see the value of a is 1, so we append 0 at the end, and again we do left shift, here it is 1, so we do a plus m. Again q0 is equal to 1 because the least significant bit is 0, so q0 is equal to 1, so we put 1 here. So we put 1 here, and after putting this 1, we again do a left shift, and as it is 1, so we do a is equal to a minus m, and after doing the 4 iterations or 5 iterations, because it is 5 bit, we get the value of remainder and quotient. This 10 represents 2, this 11 represents 3. So q is equal to 3, a is equal to 2, so q represents remainder and a represents quotient. So in this way, without restoring our values, binary division on the decimal numbers. So okay, so first we convert these decimal numbers into binary, then the number of bits can be decided or can be given. So here we use 5 bits. So using 5 bits we do 5 iterations, and using 5 iterations we have got the quotient and remainder in value of 11 divided by 3. So again, for better understanding, we use another example in which we divide 3 by 4. Okay, so here also we using the 5 bit. We adopt the same process as it is have been used in the previous example. So 13 divided by 4 represents is 3, 12, 1. Okay, so the value of accumulator at the end will represent the remainder, which is 1, and the value of q, which is dividend, represents the value of, so the value of a represents 1 and value of q represents 11. So we adopt the same process. First we check the value of a, which is 0, so we do a is equal to a minus m. After doing a minus m, we check the sign bit of a, which is 1, so we append 0. After appending the 0, we again do the left shift because the bit is 1. So when the bit is 1, we do a is equal to a plus m, and after doing a plus m, we append 0 because the least significant bit is 1, and after appending this 0, we again do a left shift as the significant bit is 1, so we do a is equal to a plus m. As the sign bit of a is 0, so we append 1, and after last iteration, what we got 1, which is our remainder, and 3, which is our quotient. So in this way, we do not restore any value as we have seen in the restoring division, but we done a division unsigned of unsigned integer, and it can be of any decimal number. Okay, so now I come to the advantages and disadvantages of non-restoring division. So the advantage of non-restoring division is it has the faster execution as compared to the restoring algorithms. It also used in parallelism, means कि using non-restoring division we can do a parallel execution. So the parallel execution is very suitable for hardware implementation. These are the advantages. The last advantages is predictable latency. Predictable latency मतलब the number of iteration is fixed, leading to a predictable latency, which is crucial for real-time applications. And the disadvantages is its complexity and initial divisor shift. So, initial divisor shift can introduce to a delay, as it can take a more time in division process. Now, next, how it is different from restoring division. So, in restoring division, we restore the partial remainders during the division process, return the remainder to its original value, requires extra steps to restore the original result after a failed subtraction. While in non-restoring division, we adjust without restoring the partial remainders, leaves the values unchanged, we don't change the value, and use addition and subtraction operation instead of restoring the original results. It is also faster than non-restoring. Non-restoring division is faster, but the thing is that it is more complex than restoring division, as in the restoring division we save the values and we don't need to do an extra iteration of addition and subtraction. So, non-restoring division is a binary division algorithm that divides one number by the another. I think it make it clear ki how we use non-restoring division. How we do non-restoring division.